Welcome to chapter 16 on solutions. Okay. This is a little weird. It's kind of like over here. You can see me? Yeah? Okay. Henry's Law. State for me, Clement, come right here and state for me, right on camera, not on camera, on right here. Just film your audio right here. Stand right here, dude, and tell me what Henry's Law is.
Henry Law, which states that at a given temperature, the solubility of gas above the liquid, of a gas in a liquid is directly proportional to the pressure.
Thank you. So what does that mean in other terms? Simply this. Everyone, unless I'm wrong, correct me if I'm wrong, has anybody ever had warm soda? Okay. 2, how many of you have opened up a bottle of warm soda? How many people have had cold soda? How many people have opened up a bottle of cold soda? Okay, good. Warm soda, cold soda, so there's a difference, correct? So he said at a given temperature. So this is very temperature dependent, isn't it? And this is why. We're studying, what are we studying? We're studying aqueous solutions. This is the name of the chapter really should be not solution, but aqueous. It's aqueous solutions. It's a solid solute, salts dissolved into water. Correct? Easy? Yes. It's also gas solutes dissolved in water. What else is it dissolved in water? It's liquids dissolved in water, like alcohol, acetic acid, vinegar. That's dilute, all right? But the point is that if you look at gas versus solid, that's where it's dramatic. What dissolves a solid in water better? A warm solvent or a cold solvent? Mamuna. A warm solvent. Bless you, birthday girl. Okay, a warm solvent. What dissolves gas better? A warm solvent or a cold solvent? Mamuna. A cold solvent. Okay? Now, so when I open up those bottles of water, bottles of soda, has anybody ever opened up, you said you did, but a full bottle of warm soda, what happens? The gas comes out, the fluid goes all over the place, doesn't it? The gas in the water, here's the bottle. The gas just automatically comes out in solution when I open up that bottle, correct? Elvis, you with me? You know that, right? And it just simply comes to the surface, and because of hydrogen bonding, it just brings everything, all the water with it. Yeah? It just makes a complete mess, doesn't it? A complete mess. Or you shake the soda, right? And then you open it, and it goes all over the place. Correct? Same idea. Okay? So, but, let's take warm soda, for instance. We'll take warm soda. Here I have 2 bottles of soda. I'll just make them square like that. I'm terrible at drawing. Okay. They're exactly the same volumes. If it doesn't look the same, it's because you're simply seeing it incorrectly. Okay? Phone's down, thank you. Okay? Now, this is open. That's open to the air. Right? It's open to the air, correct? What's the pressure inside that? It's going to be what? It's going to be, what's the pressure? If it's open to the air, what's the pressure inside? It's going to be atmospheric pressure, right? It's going to be one atmosphere, right? Or we could say 101.5 kilopascals. Correct? Okay? Right? This is 5 atmospheres. I'm going to go crazy. Now, this is warm, right? If this were a clear bottle, what would you see? What would you see? What are you seeing visually? It's clear liquid. And what do you see? Tell me what you see. Nothing? You see, it's transparent, but what do you see? It's soda. What do you see? But what do you see? You see what? No, you can say what you see. It's okay. There's no wrong answer. Air bubbles? Air bubbles? This is soda, right? You drink soda with air bubbles? What kind of gas bubbles? Anybody know? What kind of gas? What kind of gas? CO2, yeah, CO2 gas. So let's put them over here. All right, we'll put them here. Okay, so this is 1 atmosphere. And you see bubbles, right? Going to the top, right? Right? You see fizzing, right? You see some fizzing, correct? Yes or no? Yeah, you see fizzing, right? So, but in here, it's closed. 5 atmospheres, maybe 2 atmospheres. You know, let's not go crazy. We'll make that 2 atmospheres, okay? Double. But it's closed, right? It's closed, correct? It's closed, is that okay? So what do you see? What do you see? What do you see? Thank you. What do you see? What do you see? What do you see? What do you see? Here it is here. It's a bottle. And it's clear soda. And the top is on. It's on the shelf in the store. You go buy soda. It's been sitting there. What do you see? No, you can say it's expanded from what? How do you know what it was? Yeah, it's hard, right? It's hard, right? Okay? If you squeeze it, it doesn't squeeze, does it? Right, yeah. So what can you say about the pressure inside the bottle? It's higher, right? And we said that it was going to be 2 atmospheres, so that makes sense, right? But what do you see? The bottle of soda is sitting on the shelf in the store. It's a clear bottle. It's a clear liquid. We know carbon dioxide is dissolved in there. Right? We know that. But what do you see? You see nothing. You just see a liquid, right? You have no idea what the liquid is. It could be alcohol. It says it's soda, but it could be anything, right? All you see is that clear liquid. So, I have 2 bottles. I have this bottle at 1 atmosphere, and I have this bottle at 2 atmospheres. Which one has more gas dissolved in it? A or B? Which one has more gas dissolved in it? Yeah, B, right? B, Mariam, you awake back there? Excellent. Yeah. So let's look at the relationship that relates solubility and pressure. And we know that's the relationship. And we know that by Henry's law. That if I increase the pressure, I'm going to do what to the solubility? I'm going to increase it. It says it right here. This is 1 atmosphere, and I have a certain solubility. It's right there, correct? I double it. What am I going to do to the solubility? I'm going to double it, aren't I? Yes or no? Yeah, of course. Why am I saying that? Because look, you do the experiment every time you go buy a bottle of soda. It's right here. That's it. How many phases do you see? What is the definition of a solution? 2 or more substances, 2 or more phases combined to form one phase. How many phases do you see here? How many phases do you see there? You see 2. But don't you see the liquid and the gas? You see 2, right? Here, you see just the liquid, don't you? So here is a solution, higher pressure. If I open that, I know the gas is going to come out. So I know that as I increase the pressure, I'm going to increase the solubility of the gas. So now we have 2 things. How can you increase the solubility of a gas in a liquid solvent? I can reduce the what and increase the what? How do I increase the solubility of a gas in a liquid solvent? What 2 things can I do? What 2 things do I do? Okay. I cool the solvent, cold solvent, I bring down the temperature of the solvent, or I increase the what? I increase the pressure. Okay, good. You get it? Yes. Item. The question was, in summary, what 2 ways do I have to increase the solubility of a gas in a liquid solvent? I can cool the solvent or increase the pressure. So I get rid of a lot of this stuff, can't I? That's your introduction to Henry's law. Pretty good? Good? Yes? What does... Did you look up the word immiscible? My problem children here. Did you look up the word immiscible, Mamuna? Miss, I don't want to sit too near the front. What does immiscible mean? Yes. What is it? Yeah, it's not forming a solution. All right, let's write down the definition of a solution, okay? A solution is, we're just going to make this up as we go along, okay? A homogeneous combination of 2 or more substances such as carbon dioxide plus water or alcohol plus water. A homogeneous combination of 2 or more substances resulting in a single phase Okay? Resulting in a single phase. Okay, let's make that happen. Let's put it over here and we'll film this. Okay, it says a homogeneous combination of two or more substances, carbon dioxide plus water or alcohol plus water, resulting in a single phase. You okay with that?
Yeah.
Okay. And what happens is that like the alcohol will actually dissolve in the water, or the salt will actually dissolve in the water. But what does immiscible mean? Come up here and read this to the thing. You're going to be our resident audio definition man. Stand here. Can read that into the microphone. What is immiscible?
When two or more substances do not form a homogeneous mixture when mixed.
Say what?
When two or more substances do not form a homogeneous mixture when mixed.
Good. Excellent.
Should I stay up here?
So it doesn't form. You can sit there if you like. It doesn't form a solution. That's a pretty good one. Now, let's use this board up here to explain the next few words. The next few words are pretty straightforward. Let's say this is around 40 and around 45 grams per 100 grams of water. Okay? I'm guessing, but this is about right, I think. Look up solubility curve for sodium chloride in 100 grams of water. Put all that in. Solubility curve, sodium chloride in 100 grams of water. You get one? Let me see it. No, I need a picture, dude. Let me see it, man. All right. This one says, I don't want to say something that's not true, even though, yeah, it runs around, I thought it was higher than that. Let's do this one. All right, so it's going to be around 35 to 40. Okay, so let's say 30 to 40. So this will be 30. This will be 30. And this will be 40. And it's going to be like this. Ish, right? This is going to be 0 degrees, and this is 100 degrees, right? Yes? See that? Okay, so the way you do this is this. You go to a certain temperature, let's say 50 degrees, and you say to yourself, okay, well what mass of sodium chloride can I dissolve in 100 cubic centimeters of water, 100 grams of water at 50 degrees Celsius? How would you do that? How would you determine that?
Could you repeat the question?
No, you don't need to calculate it. Just read it right off the graph.
Could you repeat the question?
How many grams of sodium chloride can I dissolve in 100 grams of water at 50 degrees Celsius? You simply go like this. Let's say that's a perfect curve, okay? And you just go like this. Let's use red, okay? What you do is you say this. You go 50 degrees, and you go like that, right there. You See? And then you read that right off the graph. What's this with the 8s?
35.
What is it?
35.
35? Yeah, around 35, I guess. I don't know. I mean, that's not perfectly drawn. I have to explain a couple things before we push on, okay? Notice, and you saw this last chapter, it's going to be mass in grams of solutes over 100 grams of water. Okay? Right? This is the solute and that's the solvent. Notice that's a ratio. You see that's a ratio? Yes? A ratio that expresses solubility is called the what? Is called the what? The ratio that expresses the solubility of a solute in a solvent is called the, this is the same class that has done their outlines, it's called a what? It's called,
You said
It's one error.
it's a concentration. Concentration is a quotient or a ratio made of a numerator, which is the solute, and a denominator, which is the solvent. Clear? Yes? In this particular case, it's mass of solute over 100 grams of solvent. So here it's going to be this. Okay? So I'm saying to you now, and we'll do some problems. I'm saying to you now, simply this. That's a perfect graph on the board. The lines are perfectly straight. You simply need your eyes checked. Perfect. It's a perfect graph. Perfect. And you can read that graph. It's perfect. Okay? So I can say 50 degrees. I go up here, and I can read that. I can read whatever that is. I can read 39 degrees, what's the solubility, correct? Yes or no? Now, if I have, those lines are lines of what? Look guys, it's the most solute you can put in the solvent at that temperature. When you take a sponge and you fill it with water, so it just starts dripping. You say that sponge is blank with water. You say that sponge is full of water. You say that sponge is what? Starts with an S. Saturated. So you say that sponge is saturated with water. Correct? I'm saying to you here that at 50 degrees Celsius, that's going to be 37 grams, I'm making this up, 37 grams of sodium chloride will dissolve in 100 grams of water, and that's a saturated solution. That's all that I can put in there, right? If I put less than that in there, what kind of solution is that? If I put less than the saturated quantity, what is that? If I put less than the saturated quantity, what kind of a solution is that? Starts with a D. It's on the board. It's a generic term. You know the word. You know what the word dilute means? Yeah. If you take your favorite soda, right? Name me your favorite soda. Soda. Really good.
sorry.
What's your favorite soda? Coca-Cola. Okay, good. So I'm going to take your favorite soda, and I'm going to put twice the amount of water in there. What did I do to the stuff that's dissolved in the water? What did I do to that solution? I diluted it, right? Yes? So, down here, if I put only this amount of sodium chloride, what's that solution called? That is a dilute solution. So that line is called the line of saturation. What's below the line? What's below the line? The area of dilution. It's the area of dilution if you're below the line, correct? What about if you're above the line? I'm going to tell you a story. I don't have this chemical, but it's a great experiment to do. It's great. Can I erase this? Is that okay? No, I don't want to erase this. Can I erase this?
Yes.
Okay. Let's say I have this graph. This is grams per 100 grams of water. Where's that solubility curve you had, Clement? Where is it? Show me the picture. Looking at backpacks? Yeah, do it. Get it back, image. Yes? You have one? All right, I want. So at 40 degrees, it's around 30. I was almost right. Like 36.8. Okay, everybody come and look at this. Come up and look at this. This is great. Come on, guys. Come and look at this while I'm doing this. You get it? Here, man. Why is it so dark for them? Okay, let me see if I have it on here. Oh, here's one. All right, so this one goes from around 15 at 0 to 140 at 70. 140 at 70. So this is 0. So it's around 15. And then this goes to like 140, like this, at 70. So it kind of goes like this, like that. Yes? That particular salt is extremely sensitive to, that salt is extremely sensitive to the temperature, the solubility of the solvent with temperature, correct? So this is what we used to do. We used to heat the water. The name of the chemical is this. Potassium nitrate. Right, this is what we used to do. We used to take a large test tube like this, but really large around like this, right? And we used to put water in it. Misa, thank you for paying attention. I appreciate your support. So we used to put water in the test tube, and then we would warm the water up to not boiling, but near boiling, and we would dissolve in it well in excess of 140 grams. So that it would all dissolve. It would all dissolve. Maybe we would put 200 grams, but it would all dissolve at a higher temperature, right? Not boiling, but near it, like 90 degrees, right? And then I would take that solution and I would put it in one of my filing cabinet drawers overnight. I'd wrap it in plastic. I'd wrap plastic like paraffin wax on top, right? So nothing, no dust got in it. And I would put it in a test tube rack, special for that particular size test tube. And I would put it in a file cabinet, right? Yes, you get it? And I would take that out the next day. And the temperature of the room is like 20 degrees Celsius. But nothing came out. Nothing came out of fluid. It was all still dissolved, right? Now remember, I have almost 200 grams of solutes dissolved in there, don't I? Yet I'm down here. That's the temperature of the room, 20 degrees Celsius. So I can only fit this much in here, right? I can only fit that much. What's going on? Make a statement about that solution. That solution is blank. That solution is supersaturated. This is what I would do. It's very cool. I would take a spatula and I would take some potassium nitrate, just a little bit, just a couple of crystals, and I would take the salt and I would put it in the test tube. You know what happened? Everything would come out of the solution. It would all come out. I'd get like whatever, 150 grams of potassium nitrate would come out of solution like that. I would. Like that. It went from supersaturated to saturated. Like that. So, this is what I had then. Can I erase this? This is what I had. Are you ready? I had this, right? Here, I had solid, and here I had a solution of, right? The solution is saturated. What's this called? Material that goes from dissolved to not dissolved is called what? What's the material called? What's the noun? Give me a noun that defines the stuff that becomes undissolved. The potassium nitrate sitting on the bottom of this test tube is called what? Learn nothing else in chemistry. This is an important word. What's it called? Anybody? Anybody? He says, what is it? Material that was once dissolved but becomes undissolved. What's it called? What? I've now stated the question 5 times. Now you're going to what? What? It's called a what? It's called the precipitate. It's called, what is it?
There it is.
Precipitate. What's the act? The act of the precipitate coming out of solution is called what? Every time it rains, you can say this. It's called precipitation. Clear? The water that was in the gaseous phase, solution, air and water gas. The solution, humidity, whatever. When it becomes undissolved and falls to the ground, it's called precipitation. The rain is actually the precipitate. Same thing is what we're doing here. Same exact idea. Yes? I'm done. I'm toast. That's part one. We'll do part two tomorrow. Have a good day.